Welcome to week 13. This week and next week we will be seeing the Laplace transforms as promised, and sections 6.1 and 6.2 will be for this week, and a little bit of introduction to Heaviside or unit step function, which is in section 6.3. There will be a little introduction to it, and the derivations and examples, as usual, I will be presenting them with handwritten notes in the video. So let me move on. So where do we use Laplace transform? We have many uses actually, especially in your vibration or control courses that you will be seeing later. But connection with the previous courses can be made like this. In partial differential or ordinary differential equations or the differential equations course, you had seen some techniques to solve the problems, ODEs, and Laplace transform is yet another method to solve those ODEs, but in a very specific algebraic way. Okay, so it's like all of a sudden your ordinary differential equation turns into multiplications, divisions, additions, and subtractions. So in that respect, Laplace transform is quite powerful and valuable for engineers because you can easily code them into in some programs, okay, in computer programming. So we can convert a calculus problem to an algebraic problem that you can use a software to program it and solve. Okay, now particularly in section 6.3 and 6.4 we will have some opportunity to see or build new functions based on these two functions like unit step function and Dirac delta to make different inputs to our system. So to make our system more realistic and applicable to engineering problems like putting short impulses or damping problems and so on and so forth, you can use it for more complicated periodic functions, not just sinusoidals, for example, a decaying sinusoidal and similars. You can create those functions which are on the right hand side of your ODE, which is like your input, and look for the response on the left hand side, which is your regular function. So we will come to that point after seeing the simple derivations and how we will make use of these functions after this week's introduction. So let's start. We had seen before that there was something called Laplace operator. It's like the nabla square, right? If you remember. And I said to you, don't mix it up with the Laplace transform. The reason is they're completely irrelevant. But what is a transform? What is an operator? So let's have a brief look at it. An operator is something that takes in a function, spits out a function, but those two functions are dependent on single or multiple variables, but the variables are same in each case. So I could be looking at a gradient function, a derivative function. They're all putting in numbers and spitting out another number using the same variable. But in a transform, let's say our time variable in your small f function transforms into a capital F function That is in terms of, let's say, S. In this case, in Laplace transform, many of the cases we use S for frequency. And so within the transform, your variable gets changed, and since it is changed from T to S, your transform term, which is going to be appearing over here, right, down below here, is called kernel. It needs to include both of the variables. So in our specific example here, it needs to include time variable and also the frequency variable s and t. So we need to find some sort of a function which is called kernel, which makes the transformation that includes both of the variables. So Laplace transform is an integral transformation, and when you take the Laplace transform of a function, it means that you go from 0 to infinity, you multiply your function f of t uh, with some other function which represents the kernel here, e to the minus st, and spits out another function, capital F, in terms of s. And if you take the inverse Laplace of this capital Fs, you will get the f of t. So this is the basic definition that we will be using for Laplace transformations that we will derive for some of the functions. And I need to note here that there are lots of good YouTube videos on intuition behind the formula that you see over here. So the transformation kernel, and these are all explained nicely, either algebraically or graphically, actually. So let me put that parentheses here, and let's move back to our slide. So let's say I'm trying to transform a function or a waveform that you will be seeing in some control classes or vibration courses, from time domain to frequency domain. What is a Laplace transform? It is the integral of f of t, that my function, times e to the minus st from t0 to infinity. So that is to say this integral over here. And this results in a function as a function of s, say, let's say capital F of s, and that we denote as Laplace of f. So that question mark was to discover this. If we were in a real classroom setting, I would be asking to decipher this wording over here into some mathematical format, and that would be this. All right. Now, as I said before, please have a look at some internet resources on intuition of Laplace transform. They're well explained, and in some of them, where the reason why we have a multiplication by e to the minus st. But in this course, within 2 weeks, we do not have time for those explanations in details. Okay. So inverse is defined. So in order to be able, if I'm given the capital F, which would be in some of the cases would be the case, and in our ordinary differential equation solutions, that will definitely be needed, because I'm going to be going to the forward transformation and then go to the backwards transformation, and the backwards transformation is defined, and you will get your original function f of t in the inverse case, and it's linear. So that's a good property. If it's multiplied with a scalar, I can pull out those scalars and turn the addition into straightforward addition of Laplaces. So You will be able to find lots of tables in the internet or in your book which are giving the uh, Laplace transformations, basically. So if you have something in terms of t, some function f of t, then the Laplace transform of that function, which is in terms of s, are given in different tables. But here we will start with simpler functions and then build to more complex functions. And of course, we will stop at some point. For example, I will not drive the tenth one, okay, tenth one on the table, but I will be driving most of this table. And of course, you have additional tables which can be based on this original table. Okay, so this is a very common technique. Now, for example, sorry, f of t, if it is 1. One of the most important things that we have in our definitions, where did the, I'm sorry, I lost my notes for 1 second there. Now, for one of the most important things is this range of convergence, ROC. Okay, so you will hear this terminology in your control classes quite a bit. So range of convergence is meaning, we will see later, you need to really define for which range of variable t uh, your Laplace transform is valid, because for some of the t's the Laplace transform will diverge, but for some of the t's it will converge. And so there are lots of evaluations based on these, like I think stability of a signal, or causality of a signal. You will learn these and become proficient on these later in your third year. But for now, just remember that you need to really define the range of convergence for your variable ahead of time. So for a function f of t equaling 1, this is easy. T needs to be larger than or equal to 0, but let's see how we can derive this one. So f of t is 1, so Laplace of 1, I'm just multiplying it 1, this strange kernel transformation integral, and there is 1 here, I can oversee that. So let's go with the limit definitions. As I'm replacing one of the boundaries with a, and as a approaches infinity, what does this integral do? And t, remember, it's something larger than or equal to 0 for our kernel to be defined. That's a necessity. And limit, as limit a goes to infinity, this integral comes out as easy as minus 1 over s e to the minus st, and 0 to a. And as a is reaching infinity, let's see what this whole thing goes to. As it is over here, e to the minus s infinity approaches 0, this first term approaches 0, so minus minus goes to plus 1 over s, and where I really need to be careful here to really define it. If s is larger than 0, if s is larger than 0, if and only if s is larger than 0, this converges to 1 over s. If not, it goes to infinity, it diverges. So for s, range of convergence means that s being larger than a value 0. Okay, so that's a pretty important kind of concept that you need to really get used to. And range of convergence, you will hear this as rock in some resources or videos. Okay. And causality, stability discussion in the control field, you will hear this a lot. Let's take another function, e to the e to the power at. Okay, when we take the Laplace of that, what comes out? So here it is. I'm writing my integral. I'm getting rid of the limit from this point on, but you can assume that the limit works here too. So e to the a minus s, obviously, a is some number here, and dt. So what is the integral? 1 over a minus s e to the a minus st, 0 to infinity. And now if there's a condition here, if s is larger than 0, if s is larger than a, then e to the power a minus s is a negative value, or it will converge to 0 if you meet this condition, and 0 minus 1, why 1? Because e to the 0 is 1. I think I missed that point over here. Something like e to the minus s0 is going to be 1, so this is going to be minus 1 over s. So similarly over here, it will converge to 1, and this will be minus 1, and that will be 1 over s minus a, where s is larger than a. Okay, so that's a good thing, and we can put that aside. So wherever I have my green square, I have now driven one of those formulas in my table. So let's look at the sine 80. Is that the one that is in line? Let's see. Yes. So let's look sine 80, and here I need integration by parts. Just remember this. If you take the derivative of multiplication, you have the derivative of first one, second one, plus first one, and the derivative of the second one. And from here, if you have something expressed in uv, if you take the integral, so if you take the integral, uv becomes this. And if you have one of these, which is like integral u prime v, then it's going to be uv minus integral uv prime. So we will need to use this thing 2 times in derivation of the Laplace of sine 80. This will take a little bit of time. So e to the minus st and sine 80, I am randomly choosing e to the minus st as the u prime, and so u is minus 1 over s e to the minus st. And v prime, that's easy because sine 80, if you take the derivative of that, a cosine 80. And if we continue here, the first term is gonna be uv. What is uv? Minus 1 over s e to the minus st sine 80. That's over here. And minus a over s e to the minus st cosine 80 dt. So that will be u prime v. If you now use this identity integration by parts for a second time over here, all right? So I'm going to leave this on the screen for a while for you to note that down if you need to. Okay, I'm not going to spell out everything over here, but maybe take a sip from my water. So hopefully you can now understand that we are repeating, once we sort out the terms, we are now repeating what we had originally called over here y. Laplace of sine 80 is this. Since sine and cosine and e to the power minus st type of exponential functions are kind of resulting in similar functions as you take derivatives and integrals. 2 times derivative of a sine function is going to result in sine, and so you go back to the original function. That's a pretty nice identity for these types of periodic functions. And if you take that y to the left hand side and open up the first term and join it with the term that you have here, sorry, this cosine term here, you can now look at the thing one more time. Where does it converge as one of the limits goes to, or boundaries goes to infinity? E to the minus st goes to, again, 0. And if you write 0 times this is 0 minus, and put the boundary 0, where does it go? Let's see. E to the minus st is going to go to 1, minus 1, that's good. Sine 0 is going to be 0, and cosine 0 is going to be 1, so a to the a over s squared. So if you do some simplifications over here, you will see, well, s squared, a squared over s squared is going to be equal to a over s squared. And y is going to be equal to, if you cancel these out, a over s squared plus a squared. So the Laplace of sine 80 is going to be a over s squared plus a squared. So this is something I will be able to use later, picking up from my table. And cosine 80, we could derive the cosine 80 in a very similar fashion and end up with s over s squared plus a squared. But I'm going to introduce the Laplace of derivatives first and then use a trick from there to find out what the cosine of 80 is by looking at the Laplace only. So that's just another little trick that you can fancy as a mathematics reader maybe, okay? Now let's go back to our slides. If we go back, we will see, we are seeing, we have talked about this function f of t being equal to 1. We have talked about e to the at, e to the power at, sine at or omega t. That's our frequency. That's something you should be aware of. So whatever that constant we have here can be taken as our frequency. So in your frequency domain, actually, that turns out to be our omega. So that's a good thing to know already. And we will open up all these black boxes later, one by one, as we see through. But Laplace of derivatives, let's see how can we express it. Now, if we do the same trick, integration by parts that we remembered over here, it's gone, huh? So the computer is slow. Now, if I take the Laplace of the derivative, e to the minus st, f prime t, that's my function now, and I'm going to call e to the minus st as usual u and f prime t as v prime. So v is actually f of t and u prime is something we had seen earlier. Now, if you sort the terms, what happens? This is uv, right? U times v is going to be e to the minus st ft, 0 to infinity, and then minus u prime and v, and the integral of that. So minuses cancel out. If you put infinity here, that's going to converge to 0 minus f of 0, and S Laplace ft. Why? Because this is if you pull this S out, this is exactly Laplace of ft. This is good because I can now express the derivative of a function and taken the Laplace of it, and it's somewhat turning into the Laplace of of the same function multiplied by s and minus f0. F0 is what? F of 0? That's my initial condition. Remember, whatever that time, whatever that function is at time 0, let's say, that's my initial condition. So, and this is only true if f of t is increasing or diverging slower than the whole function converging. So that's some condition, but it's generally met, so you don't have to worry about it. So if I rewrite the Laplace of f prime t, it's going to be s times Laplace of ft minus f of 0, which is the initial condition. Let's take the second derivative. So that's going to be s Laplace of f prime t minus f prime 0. So if you put back the Laplace of f prime t in here, you will end up with s squared Laplace of ft minus s f0 minus f prime 0. And if you really go to the end derivative, that will be equivalent to s to the n Laplace ft minus s to the n minus 1 f0. So bunch of initial conditions embedded here, s multiplication and the Laplace. So my derivative is kind of expressed in the frequency domain by the function itself. That's quite powerful. Huh? So we will see it now later, maybe a bunch of slides later, how we can use these in the solution of ordinary differential equations. That's the beauty of it. So there's a little note here. Laplace turns, the Laplace operation on a derivative turns the result to some multiplications by s, multiplications of my original function's Laplace with s. And not written here, but integrations can be expressed by divisions by s, and that's on the page 213 in your book. You could maybe, if we see this example, we will use that identity. Now, if you look at your these are some summaries that I have already put in the notes. Now, before using this Laplace f of f prime t, in solving ordinary differential equations, let's try to open up two more formulas from our table. So what is cosine AT, Laplace of cosine AT? Let's go back. Cosine AT, if I call that f prime t, which I could call because I know the integral of cosine AT, it's going to be the f of t in that case will correspond to 1 over a sine AT. That's good because the derivative of this is directly cosine AT. And that is equal to s Laplace ft minus f0. f0 is nothing here because there's no initial value. It's not a problem yet. And s Laplace of the original function 1 over a sine at. I can pull out s over a Laplace sine at. I have driven Laplace of sine at. It's a over s squared plus a squared. That cancels out the a's. So Laplace of at is going to be s over s squared plus a squared. That's good. Now let's move on to another function. If f of t is t, f of t is t to the power 1, if you will. In that case, I would need one identity here, which could be used. That's like the integration. So reverse of this one or this one, inverse operation of that one. How can I sort out the terms there? Laplace of f prime t was this. So let's see what is the original Laplace ft. Original Laplace ft, if you leave that alone, you pull this to this left hand side, so Laplace f prime t plus f of 0, and if you divide all this expression on the right hand side by s, you will get the Laplace of ft in terms of its derivatives. Now let's use that. Laplace of t, in this case, this is my f of t, it's going to be 1 over s Laplace of f prime t. F prime t is just 1, and plus f of 0, that's going to be, if you put 0 f of 0, that's going to be 0. That would be equivalent to, and Laplace of 1 is 1 over s. So the overall result for Laplace of t is going to be 1 over s squared. So how about t squared? Same thing, 1 over s Laplace of 2t. Why Laplace of 2t? Because that's the derivative of t squared. Derivative of t squared here. So I pull out 2, I divide by s, that's going to be Laplace of t. Laplace of t is going to be, or already, 1 over s squared. So this Laplace of t squared goes to 2 over s cubed. Now t cubed, let's do one more, and then we will be deriving the general formula for t to the power n. And that's going to be 1 over s. And what is the derivative of this? 3t to the squared, t to the power 2. And then 3 over s, because I can pull this out, Laplace t squared. And Laplace t squared is 2 over s cubed multiplied by s. That's going to be s to the 4. So 3 times 2, s to the 4. So let's generalize it. What is this? What do we see here? It's like 3 times 2 times 1. 1 is already here. That's 3 factorial. So nth power of t is going to be n factorial over s to the power n plus 1. That's the general formula that you can find in your tables. So let's open up our table. We have derivative t to the power n and cosine omega or at. That's good. Next, so the first shifting theorem is appearing in one of the sections that we will cover today, and which is about replacing the s, which is in the frequency domain on the right hand side, f of s, capital F of s, and I'm gonna shift my frequency in a certain problem that I don't know yet. I'm gonna shift the frequency by a. So if I know Laplace of ft, and we can get e to the power eat ft by shifting in the frequency domain right hand side, I'm gonna be representing that on the left hand side by an e to the power at like this. So how come this is true? Let's see the first shifting, or s shifting, or frequency. If you're dealing with the frequency, if you name your s as frequency, that's called frequency shifting. And that's quite important in signaling, right? So lots of stuff going on with this. Now, S shifting, first shifting theorem, and we are trying to replace S by S minus A. So I'm gonna claim that the Laplace of an A shifted, or S shifted, or an S shifted by A can be represented on the left-hand side time domain function with an e to the power at ft. So let's see if this is really corresponding to an S shift. So the integral that I have to write is e to the power at times e to the minus st ft. So I'm keeping my function here, f of t, and that's going to be e to the minus, that I can rewrite like a minus s, but that's equivalent to minus s minus a t, okay? And Laplace of f of t is going to be f of s, capital F of s, and 0 to infinity. That's my general definition. And if I compare these two definitions, I'm just seeing the same thing, but I'm replacing the s by s minus a if I use a function like that. So instead of s, I have s minus a. So instead of capital S, capital F of s, we have capital F of s minus a. So a shift by a in s on the right hand side corresponds to a e to the power at times f of t on the left hand side. So kind of like an exponential function that is going to be added to the tail of my function. So how does it look? Let's say Laplace, and let's see a general example here. If I want to take the Laplace of 5 sine 5t, I had seen before, this is like sine at, it is equal to a over a squared plus s squared. So if I replace a by 5, that will be 5 over 5 squared plus s squared. That will be my capital F of s. And if I, let's say, multiply this by e to the power 40 times sine 5t. So I'm interested in this particular function f of t, small f of t. That will correspond to exactly 5 over, let's expand this to 25. And the s will be shifted by how much? By 4. S minus 4 squared. So this is nothing but fs minus 4, or capital F s minus 4 for this Laplace term. So my function is shifted by 4 units in the frequency domain. 4 units in the frequency domain. Can we also write this if, let's say, I'm given a shifted, like frequency domain shifted function like this, by taking the inverse Laplace of it, I will be able to get the original function. So, this is some technique that we will be using to reach some of the original functions that we will develop in the solutions of ordinary differential equations by Laplace transformation technique. So that was it. Yes, let's continue with the example. The example is that's, I think, is that the example? So that's something like an example. I'm trying to give the example here. That's what I'm talking about. Let's see another example here. And this example is damped vibrations. And we will use something called completing the square, some just arithmetic or algebraic method to solve some of the inverse Laplace questions. And this is in section 6.1, example 5, and on page 208 in your book. So let's say I have a function like f of capital F of s 3s minus 137 over s squared plus 2s plus 401. That looks ugly. So I don't know how I can partition this function to make it look like look like something familiar that I saw on my tables, right? So I know all the corresponding Laplace transforms of these familiar functions in terms of s on the right hand side. So if, for example, I am given my frequency domain function, which is this ugly function here, I don't really know how I can express it in terms of the familiar functions. That's the problem here. I need to use something techniques, different techniques. I will show you other techniques later, but here we will try to complete it to a square. How can I do it? Well, there's this little trick here. If I pull this 1 from 400 and match it with the s squared plus 2s, like here, I'm going to see a trend. That's exactly s plus 1 squared. And s plus 1 squared, that could be useful in one of the sine or cosine functions here because I have s squared appearing. And s plus 1 or minus 1 just give me a sense that there might be an s shifting here. So let's see if this is gonna give me something. And remember, I have Laplace of sine at is appearing as a over s squared plus a squared, and cosine at Laplace is going to be s over s squared plus a squared. So the trick continues. Since I will have s plus 1 squared here, besides there will be some 400, okay, can I create that same thing on the numerator? Yes, I can. I can partition this 137, or not partition, but add and subtract 3 here, and pull one of those 3's to here, like 3s plus 1. And in that case, that will be minus 140. And on the numerator, in the denominator, I will have s plus 1 squared plus 400. That's gonna be like 20 squared. And if you take and partition these, 3s plus 1 squared over 3s plus 1 over s plus 1 squared plus 20 squared minus 140 is 70 times 20, good, over s plus 1 squared plus 20 squared. Now, if I take the inverse Laplace of this one, in the parentheses I have s plus 1, which can be rewritten as s minus minus 1, which is equivalent to s plus 1. And that corresponds to a kind of an s shifting by minus 1, and that corresponds to e to the minus 1t, and that's common to both of these because I have s plus 1 here, s plus 1 here, so I take into e to the minus t parentheses and then read out the terms. So if I have something related to s over here and s squared over here, that's going to be a cosine after in the inverse Laplace. So cosine, what is the coefficient, like the frequency coefficient? I have 20 here, so that's going to be a. So cosine 20t, cosine 20t's, and 3 is my coefficient, scalar coefficient that appears here, minus 7 sine 20t. Why? Because sine is actually related with the a here, and that's going to be s squared plus 20 squared, or s plus 1 squared plus 20 squared, and 20 appearing on the numerator. That's going to be a sine 20t function there. So there you are. If I'm given a function capital F of s, by partitioning it and completing it to a square, like the kind of an artificial technique, in which I use my imagination, maybe I'm gonna be able to express my original f of t in terms of t's. So that's a good thing. So let's go back to our presentation. We have seen this, and this original I have put it in terms of I try to put the frequency domain function into some plot. So that looks like this. So some sort of a plot that has a dip over here and then increase. So you can think about this as a frequency signal, and that would correspond to something like this if you really expand the x from some really big minus values to big positive values. This is a small minus to some intermediate plus value. And this was kind of my frequency domain function. And if we plot the time domain function, which we found together in the notes, that looks like this from a big minus to a big plus. And if you shrink that time to minus 1.7 to 1.7, that looks like that. But remember one thing, all these Laplace transforms were valid for the values of the function or the range of t's that are positive. So in reality, my result needs to be cut from 0, and there is nothing like minus time in this type of way of looking, and this is some sort of an exponential decay. Look at this. This is an exponential decay. Do I see it in my function? Yes. E to the minus t gives me an exponential decay, and some sort of a periodic function that is like in terms of cosines and sines, and it looks like this. Okay, so my signal output signal, if you will, from that frequency domain is gonna be looking something like this. Okay, and for different times, as time goes on, I have a kind of a vibration, a periodic vibration, but what happens to that vibration? It is being damped out, right? It's damping. So this system does that. It's pretty good. Can I open up new stuff from my table? Yes, this S shifting can be expressed for both sine and cosine functions. If you actually, to be honest, by combining the 6th, 7th, and the 8th, you can already get the 11th and the 12th. You don't need these. So some of the entries in your table, actually, they're not that important. So let's give a break here, and I will continue with the differential equations or the initial value problems and the method we use there in the second part.